the ones which are already covered in highway engineering. Okay, so that's why I kept them in the end. So even if I don't cover them, I don't mind. So I don't cover them. Okay, but anyways, we started with the segment design problem. Okay, and what we did last time was find out the critical volumes. Okay, so the phases were already there, and we have to decide which phase should have which critical volume. Okay, so we decided from here the greater one, most obvious choice. Okay, do you remember how to decide from here? We got 800 from here. How did we decide? Anyone remembers? Yeah.
At every phase?
At every phase we did here. Here the phases are overlapping. So what do we do? I cannot decide A1 because A1 is overlapping with this one, right?
Yes.
Okay, and A2 is overlapping with this one and this one both. Okay, so how do you decide?
We add them together.
Which ones?
The 600 and 150.
Okay,
And 550 with 2.
okay. Yes, we added them together. We were looking at the sequence. Okay, not individual phases, but sequence. Okay, did you write it?
Yes.
Did you break it last time?
Yes.
This thing?
No.
Well, you didn't write it. So what's the use? So, but anyways, 800 from here, 300 from here, total 1100. Then we calculated the cycle length using this equation, and cycle length was how much? Did you write it? Did we calculate cycle length? I don't remember. Okay, can you calculate the cycle length? So this thing is 1100. This thing is 1100, and we have 4 phases. Okay. Rest of the things are written here. Can you give me the cycle length? Okay. How much?
63.7.
This is my total cycle length. Okay. Now, obviously, we will not keep it 63.7. Okay, because we are talking about seconds, right? So, what is 0.7 seconds? Nothing. Okay, even 1 or 2 seconds is nothing. Okay, so we round it up. Okay, now usually this cycle length is like it's almost a minute. Almost a minute for 4 phases, remember. Okay, so if you divide the 1 minute into 4 phases, every phase will take a very small amount of time, right? Okay, so we round it up higher. Okay, now you can round it up to 64. Okay, you can round it up to 65. Okay, 64, 65 is still a very low number. Okay, so when the actual cycle length is so low, close to a minute, then you round it up to the nearest 10 seconds, not to the nearest second. Got the point? If it was already 150 seconds, okay, then I will round it up less. Getting my point? But it's already very low, so I will round up more because I have more margin. Okay, so we will make it 70 seconds. Got it?
What is the limit?
For what?
For the rounding up or down?
Anything close to a minute. Anything close to a... No, we don't down. We are designing, right?
Yeah.
We cannot down.
So keep it same.
You can round up, but how much up? This is what we are discussing. Okay, so this is 63.7. If I make it 64, I'm rounding up, right? 64 is also round up. 65 is also round up. Okay, so should I stop at 65 or should I do more? Okay, so this depends upon how much is your actual value. If your actual value is close to a minute, then we do more round up. Okay, not to the nearest 5 seconds, but the next 5 seconds. Got it?
So if it is 150 point something, we keep it 150.
155%. Normally it's a multiple of 5 or 10. Okay. Now a cycle has lost time as well. Okay. Lost time means time without movement. Lost time is time without movement. We have discussed 2 types of lost times earlier. I'm not going to go into the definition, but lost time means time in which there is no movement. Okay. Now, how much is that lost time is given here. Every phase has 3 seconds of lost time. So in every phase, there are 3 seconds without movement. Got it? And how many phases we have? 4. So total lost time is 4 into 3. Okay, so out of 70 seconds, this many is without movement. The remaining is available for the movement. How much is that remaining? 70 minus this, how much? 58. Okay, now remember, my total volume was 1100, right? It was 1100. So for 1100, how many seconds I have? 58 seconds. Got it? Clear now? I have to divide this 58 into these 4 phases. Okay? Now you can see all these phases don't have the same volume, right? The volume, the phase which has higher volume should have more time or less time? More time, right? The higher volume needs more time. Okay? So I will divide them according to volume. I divide the total time according to volume. Okay. Total time is 58. Total volume is 1100. Okay. Out of 1100, 300 is here, right? So the time of this phase should be in the same ratio. So out of 1100, 300. So how much time? X out of 58. Equal ratio, right? Clear now? Okay. So how much will be X? So what was X? The green time for phase B. Okay. Green time for phase B. 300 was for phase B, right? So this is the green time. This is called an effective green time. This is effective green time. Okay. Then we have the other 3 phases. Now 800 came from here. 250 plus 550. Okay. 250 means A1, A2 both, right? 250 is A1, A2 both. 550 is A3. So I can calculate time for A3 using 550. So I replace this with 550. Okay. So how much do I get? Any question? Clear? Aisha? Okay. So now the problem is A1 and A2. I know the total volume of A1 and A2 is 250. But how much in A1, how much in A2? I don't know. Okay. Is there any volume in this figure which is only in A1? Right? So I know A1 should have at least time enough for 550. Clear now? Okay. But the problem is this 150 is not part of 800. I was using 800 in here, right? Okay, so everything was out of 800 or everything was out of 1100. Okay, but now I have to shift here. Okay, so the total should also be from here. You getting my point? 1100 was a total including this, right? Okay, so you cannot take something from here and keep the total from here. It's like I take a percentage using students of this class but the number from some other course. Will it work? So you are 12 people, I take your grade and then I divide by the number of students I have in construction management. Those are 30. Will it work? No, it will not work, right? This is what you are doing, right? This is a controller, right? So they should be both from the same side. Okay? So if I have to shift to this side, the total should also shift to the other side. Got it? Right? Okay. Now, here I don't have any problem. Okay, this is done. I have not touched this. I only have problem with these three phases, right? Okay, and from these three phases I only have a problem with A1. Okay, so now I'm just taking this sequence now. This sequence is how much? 150 plus 600 total 750, right? 750 is for what? 3 phases, right? 750 is for 3 phases. So the total time should also be for 3 phases. Okay, so now my ratio will become 150 A1, okay, upon 750, which is A1 plus A2 plus A3, okay, equals X for A1 now, okay, upon total of time for A1 into A3. How much total time I have for these 3 phases? I know the total time, right? This is total for 4. 58 seconds is for A1, A2, A3 and phase B, right? 4 phases. Out of this, how much for B? Minus 15 total. So remaining will be for, okay, so 58 minus 15.8. Clear now? Okay. So here I have overlapping problem. I cannot distinguish between A1 and A2. So I went to the other side. When I go to the other side, I have to take the total from this side, and the total of the time should also be for those all phases. Clear? Any questions? Okay. How much is X in that case? Okay, now my problem is solved because I know the total time is 58. I have 4 phases. Out of 4, I found time for 1, 2 and 3. So the remaining is for A2. Okay. How much? Okay, now here we are not covering this part, but there are minimum times for these green times as well. There are minimum limits. Okay, because now you can understand 4.8 seconds is 5 seconds, right? If the green is only for 5 seconds. I'm looking at my Instagram story and the signal is green. I need time, right? Somebody has to honk me and tell other. Got it? So there are minimum times for this as well. We are not covering this, but if the time is so less, okay, for example, I don't remember. Maybe, for example, the minimum time for green is 10 seconds. So what will happen? This 8.4 will become 10, and this 4.8 will also become 10. What else will change? Yeah, change these times. Total time of the cycles will also change. Got it? So I will back calculate them. I will add them together, add the lost time together, I will get the new cycle time. Got it? Okay. So this is how you divide the green time. Okay, this is what I was doing here, the ratio. Okay, total green critical volume for the phase, total critical volume. Okay, this is what I was doing. If you go back to the previous lecture, you will see how to convert this green into the green light time, capital G. This is called effective green. Okay, the one which you see as a green light is not effective green, that is actual green. Okay, this is number 8, right? This is number 8. So if you go to number 7, action number 7, you will see the equation how to convert a small g into capital G. Basically, you need lost time and yellow and all that time. We already covered these things in the previous lecture. Okay, the last part of signal timing is to know if this timing is enough for pedestrians or not. Okay, we need to check if the timing is enough for pedestrians or not. So first of all, we need to calculate how much time the pedestrians will need. Okay, so GPI means pedestrian required green time in phase I. Okay, pedestrian required green time in phase I. Now, if I am pedestrian, okay, if I have to cross this road, I will move in this direction, right? I am crossing this road. Okay, so I will move when these vehicles have green. Okay, so when these vehicles will have green, they will start moving, I will move with them. Got it? Okay, so my phase is which one? The one which is parallel to me. Okay? Okay, so I will be that phase, the parallel phase. Okay, now pedestrian green time has two components. One is called pedestrian walking time, the other one is called as pedestrian clearance time. For walking time, you see a table here. It depends upon the area. Okay, so if the area is too busy and the intersection is very long, then the timing will be higher. Make sense? Okay, too many pedestrians, we need more time, right? And the intersection is long, I need more time to cross. So that's why you see high volume areas, long intersections, okay, they need more pedestrian time. So this is for PW, pedestrian walking time. Then we have pedestrian clearance time. You have seen pedestrian signals, right? Okay, so before they close, before they become red for pedestrians, before they become green for us, what do? They blink. This is called as clearance time. That blinking is called clearance time. Now blinking is for what? Like if I am the pedestrian, I am crossing. My signal starts blinking. What do I do? Move fast. Move fast, obviously. Or say your child and prepare for that. Okay. But anyways, moving faster is a logical option. Okay, so pedestrian clearance time, then we take like slightly higher speed of the pedestrian because they know that. Okay, and we are also assuming that the people behind them will stay. Okay, so clearance time can come from length they have to cross upon their speed. Length upon speed gives you time, right? Distance upon speed gives you time. Okay. So what is L? Length they have to cross. Okay, and speed, SP is the pedestrian speed. So for pedestrian speed we have some guidelines, normally 3 feet per second or 3.5 feet per second, like around 1 meter per second. Okay, around that value. But these are standards given otherwise. Like in Pakistan, we used to have, I used to teach the course of traffic engineering, and there it was very different. Because we had another department. Okay, we had another degree program. You are in civil, right? So we had civil and we had something else. And that something else was more focused on transportation. Okay, they have a department like this in Saudi Arabia as well. In Imam Abdul Rahman Faisal, I think Imam Abdul Rahman University has in the MAM has a department which is for transportation only, degree only for transportation. So even in Saudi, when I was teaching assistant there, they used to have some labs, like you do for surveying. You go in the field, right, with the equipment and you take the readings and so on. So we used to have this in traffic. Okay, we used to go out on the roads with the students. The students, okay, now you will do this study play. What you did for your term project, right? This is how we got the idea for the term project. That you have to go in the field and do some studies yourself. But there, those studies, one of those studies which we were doing in Pakistan was for pedestrians. And obviously, pedestrian study we used to do inside the university, right? Okay, and you know, everybody's friends. Okay, so you are recording time and somebody is passing. So they stop. We will not pass. Okay, so there are more people who are taking time than people who are crossing. Because nobody wants to go now. Everybody wants to see how much is the time. But anyways, the point is you can do pedestrian studies to know the normal speed. Okay, so SP can be found like this, and L you can measure. You measure the width of the road for your towers, right? Same thing can be done. Okay. Once I got GP, I have 3 options. Okay, in terms of safety. Now, if I am crossing, okay, I will start crossing when the signal is what? Green. Okay. After green, the signal will become what? In which universe? After green, it becomes what? Yellow. You don't see yellow, huh? Color blind. It becomes yellow, obviously. After green, it becomes yellow, right? I'm talking about the normal intersection, not the pedestrian signal. Okay. Because we are talking about checking for the pedestrian time. Okay, we are checking. We already designed the signal, right, for the vehicle. So after green it becomes yellow. Okay. Can I keep on crossing during yellow? If I am on the road, can I keep on moving? Is it safe for me to be on the road during yellow? If the green was for me, the signal became green, I started moving. Okay, now I am in the middle of the road. It is yellow. Is it safe for me or not? No. Why not? Still same. It's yellow for who? Same car, right? This signal became green. These cars are moving. So I started moving. For these cars, the signal became yellow. But still these cars, right? They are still moving, right? So I can also move. These cars are still stopped, right? This side is still stopped. Okay. After yellow, it will become all red. Okay. All red means what? This one is red, and this one is also red. Okay. Because this one is red, it's still safe for me, right? Okay. Still safe for me. Okay. So theoretically, I'm safe during green, I'm safe during yellow, I'm safe during all red. Because in all these three timings, these cars are not moving. The cars which are coming from the other side, they will not start moving yet. Got it? Okay. Now, if the signal became all red and it finished all red. Now, even if I'm 2 steps behind, it's dangerous, right? Even if I'm just 2 steps behind, because these cars now will now start moving, right? Can you take this chance? We shouldn't, right? Okay. So what do? You can check instead of if GP can be within green and yellow, because after green and yellow, I still have 2 extra seconds of all red, right? After green and yellow, it will become all red. Okay, so this is my factor of safety. The all red becomes what? My factor of safety. Got it? Okay. Now let's say at some signal, I found the green, only the green is enough for GP. Now it became more safe, right? Because after green, what will it become? Yellow. Then after yellow, it will become what? All red. All red. Red is not safe for you. All red is safe for you. Okay? So if my green GP was only equal to green and yellow, then my factor of safety was all red. Okay? Those extra 2 seconds were my factor of safety. Okay? But if my GP is equal to only green, then yellow is also my factor of safety, and all red is also my factor of safety. Got my point? Okay? So theoretically, if GP is equal to green, yellow plus all red, I am still safe. Okay, but I don't have any factor of safety now. Okay, so if a pedestrian was crossing and he had some problem with the leg, he was, limping or he could not walk properly, so he is slower now than your time. For this guy, you don't have any factor of safety. Right? Okay, but if I made the green equal to green plus yellow, green of pedestrian is equal to green plus yellow of the cars. Now, this slow pedestrian has now 2 extra seconds of factor of safety. Even if he is late by 2 seconds, he is still safe. Got it? Okay. And if my green is only equal to green of the cars, then I have more factor of safety. If the slow pedestrian is late by even 4 seconds, he is still safe. Got it? Clear? So these are the 3 options we have. One, without factor of safety. Green equals to green, yellow plus all red. Second one is all red is your factor of safety. Third one is all red plus yellow is your factor of safety. Got it? Clear? So in every case you are increasing your factor of safety. So this is an example of if you do the check then and you found that there is a problem, then what you should do. Okay? So first of all, green, yellow and all red time is given for each phase. Lost time is also given for each phase, and then we have the pedestrian required time. Okay, so they already used this equation. They already used this equation, GP, and they gave me the value of GP. Okay, now according to their standards, they are saying if pedestrian time is equal to G plus capital Y. Capital Y is both of them together. Now see, this one is small y, right? So small y is yellow. Capital Y is both of them. Clear? Okay, so wherever they use the term capital Y, it means green plus all red. If they use small y, that is only yellow. Clear? Okay. So, pedestrian required time for phase A, 20 seconds. Okay. Green time of phase A, 40 seconds. Pedestrian only needs 20 seconds. You are giving green time double of that. Enough, right? More than enough. Okay. The pedestrian only needs 20 seconds and the vehicles already have 40 seconds. As green only. the green time itself is enough for the pedestrians to cross. They don't need yellow and all red. Got it? Clear now? Okay, now look at phase B. Phase B. Pedestrian required time how much? 30 seconds. How much green we have? 15. Now during green he cannot cross, right? This pedestrian cannot cross. Okay. If I add yellow, can he cross now? No. 15 plus 3, 18. It's still not 30. Okay. If I add the all red as well, is it enough? No. So even if I go to the last second, he still cannot cross. So now, can we leave it? Can we leave it? Today is the last lecture, we should leave it. Right? They are not even students here. Nobody would know, somebody else. Huh? We should leave it? This is in my mind, yes. Let me go home, then we could practice. Okay. Anyways. So now the problem is we are 10 seconds short. Okay. Green plus yellow plus all red should be at least 30 seconds. Got it? Right? Okay. Now, so we have to make it 30 seconds. We have to make it 30 seconds. Okay. Now, in order to make it 30 seconds, which timing can I increase? I need 10 seconds more, right? Where should I add it? Where should I add these 10 seconds? Green time, obviously. Okay, we do not add any yellow or red. Okay, even if it was 1 second. Even if it was 1 second, we'll add it in the green time. Okay, I need this total to be equal to 30 seconds. Got it? Okay. Now, this is actual green, capital G. Okay, I told you, I give an example here. If I had to increase this time, then the total should also increase, right? Okay, so I know I have to increase this time to make it 30 seconds. If I increase this time, then the total should also increase, right? Getting my point? If you increase one time, then the total should also increase. Okay, so what are they doing here? They are increasing the green time. So green plus yellow plus all red should be equal to 30. Okay, now if so I know yellow and all red, right? Yellow and all red is how much? 2 plus 3, 5 seconds. Okay, so GP plus Y should be 30 and Y alone is 5 seconds. So how much is GB? 20. Okay, 25 seconds. This is actual green. Okay, I have to make it effective green. Okay, if I want to calculate effective green is, the equation is already there in the previous lecture as well, but I will tell you, actual green equals to, effective green equals to actual green plus yellow and all red minus lost time. Okay? Do you know actual green? Yes. Do you know yellow and all red? Yes. Do you know last time? Yes. Okay, so if I put all these values here, 25 plus 5 minus 5. Okay, so now I know how much is the how much is the total, how much is the actual green and how much is the effective green for this phase. Now we said we need to increase the total time as well, right? Okay. So now I will increase the total time. Okay. First of all, I should know how much is the current total time. Okay. So total time will be green plus yellow plus orange, right? For both phases. Okay. So phase A green, yellow, all right. Phase B green, yellow, all right. Clear or not? Okay. Now this time should increase with the same proportion as you have increased the green time of phase B. Okay. Now the old green time of phase B, if I calculate the old effective green time of phase B, old effective green time of phase B. So I'll use the same equation on the old times now. Okay. So I'll call it G dash, old one, actual green 15 plus yellow plus all red minus toss time. Okay, 15 seconds. Clear? This is the old effective green time of B, and this is the new effective green time of B. Okay, how much I increased? Okay, I increased by this much, right? It was 15, I made it 25. Okay, so the cycle total time should also increase by same ratio. Okay, so the old cycle is how much? 65. How much will be the new cycle? Clear enough? So the new cycle is 108 point whatever. Okay. Will we keep it 108.3?
No, 110.
110. Should I make it 115?
50?
15, 115. Should I make it 115 or should I just keep it up to 110?
110.
Why?
Because it's not close to.
Yes, it's already very high, right? So I don't have to go very high for the rounding up. Okay, 110 seconds. Clear? Clear? Okay, now what is missing? One time is missing. I did not calculate one time. I calculated new time of phase B. I calculated new total time of the whole cycle. What I did not calculate yet, what is missing? What is the last thing I need to calculate?
GB.
GB already have. You calculate GB, right? According to pedestrian time. You said it should be 30 seconds, right? Oh, sorry, the total should be 30 seconds. This is for B, right? So what is missing now? Pedestrian already given. What is missing? You have B, but you don't have what? You have B, but you don't have. There are only two phases, right? You have new time of B, right? Do you have new time of A? You don't have, right? So we need to recalculate the time of A as well. Because the old time of A was according to the old cycle.
This one C dash is the total.
Total.
Of the
Whole cycle, both. Alright? Clear?
So it will be 110 minus
110 minus the time of B minus the yellow and red of B, then minus the yellow and red of A, and the remaining will be the green of A. Okay? So 110 equals to 25 plus 3 plus 2 plus new time of A. I don't know yet. Plus 3 for phase A. Plus 2 for phase A. Okay, so this will give me a new time of Okay or not?
But we only change the time of phase. So
But you change the total as well with the ratio. You change the total as well, right? Okay. Now what is the logic behind it? First of all, give me the value.
So it's equal.
75 seconds. It was how much? 40. It became 75. Right? Okay. So, first of all, two things. First, there are only two phases here. Okay, so I will do it like this. Okay, but if there were four phases, like the previous example, the one which we did, if there were four phases, then this thing will not work. You have to take the ratio. Okay, with two phases, because you know everything else, right? There were two phases. I already know this one, so only unknown is this. Okay, so this thing can work because this equation only has one unknown, it will work. Okay, but what if I had four unknowns? Then, if I had four phases, from four phases, okay, you know this one. Then you have three unknowns more. Can you solve it with one equation? We cannot. Okay, then you have to go back to the ratio approach. Okay, I will show you the ratio approach now. Okay, still it's for two phases. Okay, so in the old time, my cycle length was 65, right? 65. Out of 65, how much for phase A? 40. Okay. Then, in the new time, my cycle length is how much? 100. Okay. You get GA. Clear now? Okay. So, if I had, for example, GA1, another one, okay, then I will replace the old time of GA1. Okay, so if I have 4 phases, 5 phases, 10 phases, I can keep on applying this ratio and just keep on changing this one. Got it? Okay, so with 2 phases, this one and this one both will work, but otherwise you have to go for the ratio approach. Okay, now the question is, if I just change the time of phase B, if only phase B had a problem, why did I change the time of phase A? This was the question, right? Why I'm messing around with phase A1, phase A, when the problem was only with phase B. Now the signal works by dividing percentage of times into different directions. Okay. Now the total is always how much percent? If you are dividing percentage, if I add all the percentages, I will get how much? 100, right? It should always be 100. Okay, agreed? Agreed or not? Okay. If I increase this time, okay, which was 20% of the total, okay, increase this time, which is 20% of the total, but I did not do anything with this one. Total is always how much? 100, right? This was 20%. I increase its value, not percentage, value. If I don't do anything with this one, this will not remain 20%, right? This will not remain 20% because 15 was the 20% of this one. So if I make it from 15 to 25, now it is not 20%, right? It is more than 20% if I don't do anything with this one. Getting my point? Okay. So I increase the total as well. Okay. So this one becomes 20% of the new total now. This one becomes 20% of the new total. So 25 is the 20% of the new total. Correct? So they should be, if this was 20%, Then this is how much?
80.
80. Okay. So how much is the new 80% of the new total? This is what we calculated, 75 seconds. Got it? Okay. Signal, we are taking ratio, right? Ratio means what? I am dividing according to percentages. So if I change a number, the percentage will not remain the same. Okay. So if I just change one number, I don't do anything with anything else, the whole percentage is disturbed. Okay. Clear now? Now what actually will it do? I don't change it. Okay, 40 seconds was enough. 40 seconds was enough for phase A, right? I calculated the timing of phase A, it came out in 40 seconds. 40 seconds was enough for the cars, 40 seconds is enough for the pedestrian. So I won't change it. I will keep it. Okay. Now if I do it, okay, then what will happen? Phase B was green for 15 seconds, right? In 15 seconds, phase A is red. When the signal is red, a car comes. What will it do? It will stop. Okay. If the signal is red for 15 seconds, you have a queue of, let's say, 8 people. Okay. In 15 seconds, I got a queue of 8 people. Now, if I increase the green of the other signal, I am increasing the red for this one, right? Okay. So now I don't have green of 15 seconds. I have green of 25 seconds now. Okay. So will the queue remain the same? No. Okay. So the 40 seconds were enough for the queue, which was only in the red of 15 seconds. Okay. So when you increase the green time of this one, you increase the red time of this one. So more red time means long queue. So they should get more time as well, right? Otherwise the queue will remain. Permanent. Okay. So if I touch one phase and I don't do anything with the other phase, it will disturb the percentage. Percentage meaning the queue is getting longer here. And that longer queue needs more time now to move. Got it? Clear? Any questions? Okay, so this is the end. As I said, the remaining topics are from highway engineering. You can have a look. No problem.